In this video, we're going to learn how to tackle probably the most complicated thing that we're going to do this year called optimization. Conceptually, it's easy. Practically, it's pretty tough. Okay, going to be similar to related rates, but the only way to get better is just to practice. So I'm going to kind of go through some of these notes, and then we'll hop into the examples. We'll probably only do the first two examples in this video, and then the next two will be in the second video. Okay, so whenever we're trying to optimize something, that means either make it as big as possible to maximize it, or to make it as small as possible to minimize it. So this is going to be similar to something we've done in the past, right? It's defined maxes and mins. We know we have three different ways to do that. We have the candidates test, which is typically what we do to find absolute extrema. And then we have the first and the second derivative test. But those really only work well for the relative extrema, right? So our first ideal test that we're going to be doing if we're trying to find an absolute max or an absolute min. The test that we would love to do is the candidates test, because that one's the one where you make the table, right? You collect all the candidates, you test them by plugging into the original function, and then you can easily see which one of those gives you the biggest output or which one gives you the smallest output. Now, when we were doing the first derivative test, remember, that's the whole process where you find the first derivative, set it equal to 0, collect your critical points, then we throw them down on that sign chart and we test for positivity. And we know positive means f is increasing, negative means f is decreasing. And there are some situations and circumstances where this first derivative test could give us an absolute max or an absolute min. For instance, if I have a restricted domain, let's say just 0 to 2, and if the function changes from increasing to decreasing, well then I know where the absolute maximum is. If the function starts and then is increasing, then goes down and is decreasing and then ends, you can kind of tell that both the right and the left sides, those would be relative low spots. They're not relative mins, since your endpoints can't be relative, but those could be potentially the absolute minimums on the left or on the right. But I know if the function was increasing, then turns and decreases, since there's only that one critical point in the middle, and both of the endpoints would potentially be mins, I know the absolute max has to be at the same value where the relative max, right? Because the absolute extrema is either one of the endpoints or one of the relative extrema in the middle of your interval. And if there's only one relative max and your endpoints are both low spots, then you know that relative max must also be the absolute max. Kind of similar, but vice versa. If your derivative only changes once from negative to positive, so if your function only turns from decreasing to increasing to once, you know the endpoints would potentially be maximums, and that absolute minimum would have to be where you have the relative min. But let's suppose you have a more typical sign chart where if you have multiple candidates, right, if you have multiple things that could be maxes, let's say it's plus, minus, plus. So the function starts and is increasing, so that left side could be a min. Then we have a relative max in the middle, then we have a relative min in the middle, and then a function increases, then it just terminates. So the right side could be a max. I have the one relative max in the middle, and I have that right endpoint that could also potentially be the maximum value. But I wouldn't know out of just the sign chart, I wouldn't know which one of these maxes is the bigger of the two. And similarly, I wouldn't know which one of these two minimums is the smaller of the two. So the first derivative test does a really good job of telling relative extrema. It tells us where we have mins and maxes, but it can't judge and it can't differentiate between different extrema. If you have multiple maxes, the first derivative test will not tell you which one is bigger. Or if you have multiple minimums, the first derivative test cannot tell you which one is slower. The only one that actually looks at the y values is the candidates test. So even if you have two potential high spots, you should be able to easily see which one's the biggest, because you can physically look at the y coordinates. The first and the second derivative test, they are pretty good for relative because they tell you where we have extrema, but we don't look at the y values, and so we don't get the what is the extrema. So again, first derivative test, probably not a good idea to find an absolute extrema. Could it work? Yes, only in certain circumstances. Most of the time, you're going to have multiple places that could be maxes, multiple places that could be mins, and based only on that sign chart, based only on that first derivative test process, you can't tell out of those maxes which one's the bigger, or out of those two mins which one's the smaller. Okay. The second derivative test is pretty similar. It does a really good job of identifying relative extrema, but if you have multiple maxes, second derivative test can't differentiate and tell you which one's the biggest. Or if you have multiple mins, you don't know which one's the smallest. So all this page is basically to say, hey, if we're looking for an absolute extrema, the first test you should always try to do is candidates test. And then if for some reason I can't do candidates test because of a lack of information, then probably what we would jump to is the second derivative test. And then the third option would be the first derivative test. But you got to do something to justify when you're identifying something as a min or a maximum, right? Sometimes the candidates test is the only way that works. So that's kind of nice. But in general, if you're looking for a min or a max, we have the three options: candidates test, first derivative test, second derivative test. The first and the second are good for relative extrema. Candidates test is what you want to use, though, if you can, for the absolute extrema. Okay, so here is kind of a step-by-step breakthrough. Not every single question goes through every single step, but in general, when I see an optimization question, this is kind of the thought process that I go through. First thing is, what information does the problem give me? What variables are there? What units are attached to those variables? So on and so forth. What are the tools that this question is giving me to work with? And then the second thing is, does the question give me a picture? I think the pictures kind of help you visualize what's happening, helps you see the math a lot better than not having one. So if there's not a picture, I'm going to draw one. I'm a terrible artist, but I'm still going to draw one, no worries. And then you're labeling all your variables with your units, making sure we're keeping track of everything. And then the third thing, I read the question and I identify what thing, so what quantity or what value, what variable, what am I trying to optimize? And then am I trying to make it as big as possible, maximize, or am I trying to make it as small as possible and minimize it, right? So what am I trying to optimize, and then how am I maximizing it or minimizing it? Do I want it as big or as small as possible? And then here's where it gets tricky, right? 4 through 6 is kind of the meat of these questions, which is sad because it's not the calculus. The calculus is step 7. But 4 through 6, it's all your background geometry, it's all your background pre-calculus, it's all your background just general logic and problem-solving skills. What you have to do is think about, okay, what am I supposed to optimize? I need to get the equation of that thing, and then I'm going to take that derivative and set it equal to 0, because that's how you find extrema. You take the derivative, set it equal to 0. The problem is that a lot of the times you're going to end up with extra variables, and you don't want to take the derivative if you have 2 variables. So what you'd have to do is somehow figure out, how can I substitute and get rid of one of the variables and then work exclusively with only the other. Okay, so that's kind of tricky. As we practice, hopefully it'll get easier, but this is going to be challenging. Step 4, I say, what formulas, hopefully 2 of them, do I need or can I use with the information I was given? One of them is typically going to be the equation that I optimize, so that I take the derivative of. The other one I like to consider a scratchwork equation. It's just an equation that's going to tie the 2 variables together so that I can make a substitution and get rid of one, work with only the other. Right, and then I would use my algebra skills, and I would make that substitution to make that extra variable go away. Get my optimal equation, right? Get that thing that I'm trying to maximize, or get it trying to minimize. I'm going to get that thing down to 1 variable. Then I start the calculus. Take the derivative, set it equal to 0, and then we're doing our candidates test afterwards. And of course, the last one, make sure you have the right units on your answer. Okay, so this is kind of the process that I go through. Again, you don't have to follow the exact same steps. I just kind of put it here in case it's helpful. Basically, it's first couple steps. Interpret what all the question is giving to you. Then you figure out, okay, what am I supposed to spit back in return? And then it's just connecting the dots. How do I go from what they give me to what they want me to spit back? And there's only the one calculus step, taking the derivative. Everything else is algebra, trig, geometry, pre-cal, logic, right? Everything else is what makes these questions hard. The calculus, taking the derivative, is probably the easiest step, but that's okay. These questions are hard. They're supposed to be. You will only get better by doing examples. So let's go through and let's do these first 2 examples, and then we'll probably pause this video and then We'll do the last two optimization questions in the next video. Okay, here we go. First example. A swimmer is 2 miles out in the ocean and wishes to get to a town that is 3 miles down the coast, which is very rocky. The swimmer needs to swim to shore and then walk along the shore. He can swim at 2 miles per hour and he can walk at 4 miles per hour. Doesn't necessarily, I guess it does say he. To what point should he swim along the shoreline so that the time it takes to get to the town is a minimum? Okay, and it does have a little bit of a picture, which is helpful. We have this swimmer. I'm gonna ruin this picture by drawing on it, right? We have this swimmer who's out in the ocean. I don't know why they're 2 miles out in the ocean. They're probably gonna die, but it's okay. But then he's trying to get to this town. And there's really kind of the two extreme options. If the guy is a really bad swimmer, then conceivably he would just want to beeline and go straight to the shore, right, as quickly as he could. And then he would just huff it the full 3 miles over to the town, right? If you're a bad swimmer, you would want to swim as less as possible. So you would just swim straight up and you'd go straight to the town, right? We're going to assume that this person, he's treading water 2 miles out in the ocean. He's doing all this calculus in his head. He's not a dum-dum. He's not going to swim to the left and then have to walk farther than the 3. And then also, on the other case, he's not going to swim past the town and then have to walk backwards, right? Well, the one extreme is he swims straight to the shore, then walks the full 3 miles, and then the other extreme, like if this is Michael Phelps, maybe he just swims straight to the town, knowing that he's such a strong swimmer, he doesn't want to waste any time walking. Okay, so those are the two extremes. Swim straight to the shore, walk the full 3, or swim straight to the town, which means you walk 0. Right, we're going to assume he's not going to come over here, walk farther than 3, or overshoot and have to walk backwards. Okay, so we got this set up. What I'm going to do is I'm going to label this distance x. Right, x is the distance that this guy is going to aim over. And we all intuitively know that probably the fastest way to get to this town, it's probably not going to be swim straight to shore and then walk the full 3. It's probably not going to be swim straight to the town, right? If you were a really fast swimmer or a really slow swimmer, or potentially a really fast walker, maybe one of those extremes would make sense. But we know intuitively that you probably want to cut the corner and then probably aim for some little spot, swim to that location, and then walk the rest, right? We know this intuitively. If you've ever been walking out in any type of a courtyard or any type of a grassy situation, you'll probably see that if you have sidewalks that intersect, right, there's always that little cow path where people cut the corner because they're too lazy to walk all the way on the sidewalk, stay on the sidewalk, and make the 90-degree turn. Like we know people cut the corner because they want to get to their destination as quickly as possible. So we're kind of thinking that this swimmer, he's going to aim for some distance kind of down the shore, and then he's going to swim to that point, and then he's just going to walk the remaining distance. And I'm going to call this horizontal distance, right? How far he's going to aim over to the right. I'm going to call that distance x. Now, if this full distance here is 3, and if this piece is x, I know segment subtraction then. The distance that he's going to have to walk would be 3 minus x. Again, if the total is 3 and this piece that you cut over is x, then the leftover would be 3 minus x. Okay, so let's go think about some more stuff. A swimmer is 2 miles out in the ocean, yada, 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 yada. Okay, it says, to what point, so basically what's the x value, should he swim so that the time it takes to get to the town is a minimum? So we want to optimize the time, right? And specifically, I want to make that time as small as possible. So somehow, the goal for this question, I need to get a time equation based on only one variable. Then I'm going to take the derivative of that equation, set it equal to 0, and then do my candidates test, right? But I need to get an equation first, make sure it's only in one variable, then we can do the calculus. So let's think about some units. Conceptually, we should know, and if you ever have taken physics, you should definitely know, really you don't need physics, it's just common sense. Speed is just distance over time, right? If you go miles over the course of hours, then your speed is miles per hour. If you go kilometers over seconds, you're going really fast, kilometers per second. But we know in general, speed is a distance divided by a time. We don't want a speed equation though, so we don't want the speed by itself. What we want is a time equation. So I'm going to take this time, multiply it over, and if distance is the same thing, or sorry, if speed is the same thing as distance over time, multiply this and take the speed and divide it over. That means time. It's going to be equal to distance divided by speed. Okay, if you took something like feet per second and divided it by the second, or sorry, if you took the distance, which is feet, divided it by feet per second, then the times or the distances would just cancel and you'd end up with the time, right? Feet per second, or feet divided by feet per second, you would just end up with seconds. Okay, so I need a time equation, and then how I'm going to set that up is I'm going to take the distance divided by speed. So let's think about it like this. We're going to have the total time. This journey is kind of broken up into two parts. We have this first leg where you're swimming, and then we have the second leg where you're walking. Right, so the total time is going to be the time that you're swimming plus the time of the walk. Right, so that's good. Let's go ahead. The time that you swim, it's going to be the distance that you swim divided by the speed at which you swim. So the distance you swim is right here. It's this hypotenuse. It's this length of the diagonal, which if this side is x and if this side is 2, I could do Pythagorean theorem and I could figure out that that hypotenuse is the square root of x squared plus 2. Right? It's just this squared plus this squared, square root it. Okay, so I know the distance that I swim, based on this arbitrary variable x, how far you cut over, that distance is going to be the square root of x squared plus 2. That's the distance that you're going to have to swim. And then the speed for which you can swim is 2. So that expression will tell us the time of swim, right? The distance divided by the speed, it gives me the time. But we also have the time from the walking. So I need the distance that the person's going to walk divided by the speed that they can walk. I know the speed is 4, and then I need to somehow figure out how far are you going to walk. Well, we already have that, right? If you cut over x, then the distance that you have to walk is going to be 3 minus x. Okay, so a little bit tricky. Had to figure out what units, how they would line up to get a speed equation or time equation. And in order to get time, you just need to do distance over speed. So distance that you swim divided by the speed that you swim, and then the distance that you walk divided by the speed that you walk. Okay, good. Now let's look at this equation. How many variables are there? Just one, right? All that equation is based only on the variable x. So this one's actually not too bad. You only have the one variable, so we're ready to do the calculus right off the beginning, right off the get-go. Since you only have x's, just the one variable, you can take the derivative right now. Okay, well I'm gonna rewrite this just a little bit. Let's see, I have a 1/2 x squared plus 2 to the 1/2. I'm not doing any calculus, I'm just rewriting it. Plus 3/4 minus 1/4 of x. So I'm just rewriting it to hopefully make this calculus a little bit easier. Now let's go through and we're going to take the derivative with respect to my variable, which happens to be x. We're going to take the derivative with respect to x. Okay, so that's going to give us t prime. Okay, well this one's going to involve chain rule, right? I'm going to copy this 1/2, and I know when I do chain rule, this 1/2 is going to multiply to the front. So I'll have 1/2 stuff to the negative 1/2, copy in what that stuff is, and then I would need to do chain rule the derivative of that inside piece. It's 2x. Okay, so there you have it. There's your first chunk's derivative. Copy the coefficient. Then this is just chain rule. 1/2 stuff, negative 1/2. Don't forget your chain rule. Okay, so there's your derivative of your first part. The derivative of 3/4 is 0. You don't have to worry about it. And the derivative of all this is just minus 1/4. Okay, so that's good. We're done with the calculus. Aren't you glad? Now we got the rest of it, which is just the algebra and the arithmetic. Okay, so what I want to do is take this derivative. Remember, we're trying to find a minimum. I'm going to take this derivative, set it equal to 0, and then I'm going to finish the rest of my candidates test process. All right, so let's rewrite this. The 2 is going to cancel with one of the 1/2s. So that 1/2 means you have a 2 on the bottom. This means you have the square root on the bottom. And then we have the x on the top. So again, I'm just rewriting all of this stuff. The 2 and the 1/2 cancel. That 1/2, this square root on the bottom, and then the x on the top. And I'm going to add the 1/4 over. Okay, cross multiply. So I have 4x. It's going to be equal to 2 roots of x squared plus 2. You could square both sides, or if you want to reduce it, that would be fine. I'm going to reduce it first. Divide by 2. And then now we could square both sides. And then nearly done. Subtract that over. Divide by 3. So it looks like my x, remember, it could be plus or minus root of 2 over 3. Ooh, hold on. I messed up something, didn't I? Let's see, just a minute. X squared plus... Ooh, you know what I did? This is from way back when. Okay, I'm going to fix it. This was x. That was 2. So what should that radical have been if I did Pythagorean theorem? Silly Mr. Bell. It shouldn't have been a 2. It should have been a 4, right? X squared plus 2 squared. Okay, so that number should have been a 4, right? So let's fix it. Sorry, hopefully you caught that earlier. That's a 4, which means that's a 4, which means that's a 4. Nothing, it's not going to change a whole lot. That, and all this. Okay, so that was a 4. That means this was a 4. That was a 4, 4. So then I would have had 4 thirds. And then if I square root 4, you're going to get 2 over the root of 3. Okay, there we go. I was like, I'm pretty sure it's not root of 2 over root of 3. I forgot to do the Pythagorean theorem correctly. Silly Mr. Bell. Okay, so here we go. We finally got it. Sorry, I didn't want to re-record it. I'm lazy. Just fixed it, right? I had it as a 2. It needed to be a 4. Fixed it. So I got these 2 critical points. These are the values that make the derivative 0. Now, one of them doesn't make any sense. Let's think about the logical restrictions on this variable x. Right? Remember, the worst case scenario, if this person's really bad at swimming, like Mr. Bell, he's going to want to swim as small as possible, as least as possible. So you would just swim straight to the shore, and then you would just walk the full 3 miles. Now, if you swim straight to the shore, remember, x is how far you cut over, how much corner you skip. If you swim straight to the shore, your x value would be 0, right? You don't cut over any, and then you walk the full 3. So conceivably, x could be 0. We're going to assume x is not negative, right? He's not going to swim this way and have to walk farther than 3, right? But the smallest the x could be is 0. That logically would make sense. And then the biggest the x could be, if you swim straight to the town, then you basically cut over the whole distance. So the biggest that x could be is 3. So I do have some natural restrictions. I do have a closed interval for this variable. Now I'm going to take those endpoints, 0 and a 3. I'm going to take my critical point. Now notice, the negative one doesn't matter because it's not in your interval. But I'm going to take those values, and I'm going to do my candidates test and see which one gives me the biggest time and which one. Well, really, we just want the one that gives us the smallest time. So 0 and 3, they were your endpoints, your logical restrictions. And then we had this other important value, which is 2 over the root of 3, which is the same thing as 2 roots of 3 over 3. I honestly don't care if you leave the square root in the bottom, but if you want to clean it up, you could write it like this. Okay, so the calculus was to take the derivative, set it equal to 0. The function started with just the one variable, which is lovely. So I was ready to do the calculus, bunch of algebra. Now notice, you don't need the negative one because it's not in my interval. Okay, so what we would do is we would just take these 3 values and we would plug them in to this original function. Now I'm not going to waste the time to get out my calculator. I'm just going to write down what the values are. Right? So just pretend you see me typing it into the calculator. Here's what I would type in. Right? This right here. You could type in y1, and then you would do 0 into y1, and that would end up giving you 1.75. And the units for that, if you think about the time, it's miles per hours, so the units on that would be hours. And if you were to take this and plug it back into your original time equation, it would give you 1.616 hours. And then if you were to take 3, plug it into your time equation, which you could either plug it in here or up here, it doesn't matter. But if you were to plug in 3 to one of your time equations, you would end up getting 1.8 hours. Okay, so looking at this, if it said, hey, find the maximum time, well, the maximum time would be swim the whole distance, right? Since you swim slower than you walk. If you swim the entire journey, of course, you're going to take the longest amount of time. Assuming you don't come to the left, you don't go past the town, right? Assuming the guy's not a complete fool. But if you were to, for some reason, swim really fast, well, then it would be reversed, and you'd want to swim as much as possible to get there as quickly as you can. Or if you wanted to be as slow as possible, you would go the speed, the walking, that's less. Okay, so we took my 2 endpoints, we plugged them back into this original equation, and we took the critical point, plugged it back in. And it definitely looks like cutting the corner and then walking the rest. It definitely looks like that was a minimum, right? So we did end up finding the absolute minimum. Sometimes it will be a critical point. Other times it may be one of the endpoints. That's why you have to do candidates test, where you have to do something to check. But here we go. We're ready to answer this question. How far or to what point should he swim along the shoreline? He should swim, let's see, 2 over the root of 3. 2 over the root of 3, which if you want it as a decimal, I think it's, well, I don't have it written down. Oh, yeah, I do. It's 1.1547. He should swim that far, miles, down the coast, or down the shoreline, to get to the town in the least amount of time. It didn't ask what that time was. If it did, it'd be 1.616 hours. But here it just asked what was the x value, right? So your answer, you should cut that corner, and you should aim 1.147 miles down the coast. Imagine this guy, right? He's out there 2 miles in the ocean, treading water, doing all this math in his head. He's a pretty smart guy, so he's not going to cut to the left. He's not going to go over it, right? So he's going to do all this math and figure out, okay, that's exactly how far I'm going to cut over. I'm going to aim for that point, swim straight there, walk the rest, and mathematically we know that's going to get him there the fastest, right? Optimization. Okay, cool beans. Let's look at the next example, and then we'll end on this video. Here we go. Find the dimensions of a 12-ounce can that can be constructed with the least amount of metal, and then justify my answer. Justify means either do the candidate test or do something else, right? Either do candidate test or first Dorito test or second Dorito test. Do something to check your answer. Of course, if you have a calculator, let's go back to the previous one. If you have a calculator, this question's really easy. You could just plug in your original function, right? If you were to graph this, or if you were to graph this, right? If you were to do your original function in the calculator, you could just use the calculator to graph it and find the minimum point, right? Second trace, I think 3 is minimum. I don't remember. But if you graph the original, you could just trace where the minimum is on the graph. It'd be quick, it'd be easy. But if you only use this in the calculator, you're not showing any calculus. If you were to graph the derivative, you'd be looking for the x-intercept, and specifically, right, you'd want the x-intercept because the function has to be equal to 0, and specifically, you'd want the intercept where it crosses from beneath, from under, from negative to above, because we know we were looking for a minimum, and it has to cross from under to above to give you a minimum. So you could have answered this by looking at either two graphs. That would be no calculus involved. This would be a little bit of calculus involved, but we got to be able to do it by hand also. Okay, let's go back to the second one. Sorry, that was a little rambling. Find the dimensions of the 12-ounce can, and it gives us the unit conversions. 12 ounces is the same thing as 355 cubic centimeters, just my answer. And it also gives me the volume formula for a cylinder, and then the surface area of a cylinder. Let's draw a picture. Sound effects make the drawing better. Fact. Okay, so there we have a cylinder. Let's say the radius is r, and let's say the height is h. Okay, and we know the volume here is fixed. The the volume is fixed at 12 ounces, which is your 355 centimeters cubed. Okay, so that's fixed. You're not trying to optimize the volume. It says the volume is this amount. What you're trying to optimize, least amount of metal, what you're trying to optimize is the surface area. And specifically, you're trying to make that surface area as small as possible. All right, so let's think about this surface area equation. It's the area of the base, area of this base, and then you need the lateral area around the side, right? So this is pi r squared, that's pi r squared. So you have 2 of the pi r squared, so it's the area on the top and on the bottom. And then you have the lateral area. 2 pi r is the circumference, right? Circumference times the height is how you get the lateral area. So there's your formula for your surface area, and that's the thing that we are trying to optimize. That's the thing that we want to take the derivative of and set equal to 0. But the problem is that this has too many variables. It's got r's and it's got h's. Right? You could take the derivative right now. You'd have r primes and you'd have h primes. The issue is that if you take the derivative when you have r's and h's, then that derivative is going to have r's, h's, r primes, and h primes, and you would have too many missing variables you wouldn't be able to solve. So what we want to do is somehow get rid of one of these variables. Either get rid of the r's and then work exclusively with h's, or get rid of the h, work exclusively with r. But I need to get rid of one of the variables and work with the other. And that's where this fixed quantity comes in, right? The volume, which it tells me is pi r squared, the area of the base, times the height. That volume is fixed at 355. That's what I like to refer to as your scratch work equation. It's important because this is going to define the relationship between your r and your h. That's how we're going to use an equation to make a substitution. Now, I could solve this for r and then plug it in here, or I could solve this for h and plug it in the once. Either way, you will get the right answer. It's just usually one of the ways is a little bit easier. Here, I'm going to solve it for h. Right, so take all this, divide it over 355 divided by pi r squared. I'm going to use this scratch work equation, the dimension that was fixed. That's going to tie the two variables together, and then I'm going to make a substitution. So all of this I'm going to plug in for h. So I have 2 pi r squared plus 2 pi r, and then instead of h, I'm going to make the substitution, 355 over pi r squared. And then now notice, now that I've gotten rid of the h, the only variable I have left is r. So now I've got that surface area equation, but based only, dependent only on the variable r. Now, let's simplify. Don't take the derivative yet. We could, but let's simplify. Here we have 2 pi r squared. Let's see, the pi is going to cancel. One of the r's is going to cancel. 2 times 355, that's smelling like a 710. So plus 710 over r. There's your surface area equation. It's only one variable, and we simplified it. Now, let's finally take the derivative. And if your variables are, you're going to take the derivative with respect to r. Okay, so here we go. 2 times 2, it's going to be 4 pi r. That's r to the negative first, so it's going to be minus 710 over r squared. So you're just taking your derivative, just using your power rule. And then, of course, we'd want to set that derivative equal to 0 and then solve it. Right? That's the calculus. Take the derivative, set it equal to 0. Everything before is pre-cal or geometry or trig or just general logic. Everything after is usually just algebra and arithmetic. The calculus is taking the derivative, setting equal to 0. That's what we do to find mins and maxes. Let's finish solving it. Add that chunk over. Multiply this, divide the 4 pi over, so we're going to have r cubed, 710 over 4 pi. And then you would just need to cube root it, right? So r is going to be the cube root of 710 over 4 pi. I'm just going to round this, right? R is going to be about 3.837 centimeters. Then I would take that value and I would store it, right? So hit stow, bottom left corner of your calculator, stow alpha A, because we're going to need to use this, and we'd want the exact value but we can just use the stored value in the calculator, right? That's good. Don't use the rounded solution, but make sure you store it so that we're using the precise exact answer. But I took that derivative, set it equal to 0. I got this one value. Once I have the r, I would come back and I would take this number, I'd take the alpha a, the value that's stored, and I'd plug it in, and I would find out that, hey, that corresponding height that goes with it would be 7.674 centimeters. And I would store that probably in B. Okay, so again, set the derivative equal to 0, solve. Then once you solve it, plug it back in. The equation that you used to make a substitution, right? This right here, we plugged it in for the h. We substituted it in. But the equation that you use to make the substitution, that's where you plug in and solve for the second variable. So I've got this combination. I know the r being about 3.8, and I know the height being about 7.7. I know that combination makes the derivative 0. But I don't necessarily know that that maximizes or minimizes it, right? All I know is that's a critical point. That combination makes the derivative 0, but I need to know what type of critical point. So let's test it, right? Let's test it. There's not really any logical endpoints here. The r can't be 0, because if the r is 0, there would be no can. The height also can't be 0. I know the bigger it is in terms of its height, the narrower the r is going to have to be. Or the wider it is, the bigger the r, the shorter, the smaller the h has to be, right? We know that since the volume is fixed, if I make one of the values big, the other one's going to have to get small. But there's no fixed endpoint on either one, right? You could make that thing really, really, really close to 0, but there's no solid dot, there's no inclusive endpoint that says, hey, your height at minimum has to be this, or your radius at minimum has to be this. You can make it really, really small, but definitely can't make it 0, because if either of those values is 0, then you wouldn't have a can, right? So the candidates test doesn't work. Candidates test only works if you have multiple candidates and you've got to judge which one of those multiple candidates, which one gives you the biggest or the smallest output. If you only have the one candidate, candidates test is useless. So let's try to do something else. And typically, if you can't do candidates test, second derivative test is what you'd want to do, right? So let's check. Can't do candidates test, so we're going to use second derivative test. Okay, so let's see. Here was my first derivative. Remember, it was 4 pi r minus 710 over r squared. Let's take the derivative again and get the second derivative. It would be 4 pi. Now this should be r to the negative second, so that negative 2 would multiply, so it would have a plus 1420 over r cubed. Right, so taking that second derivative is not too bad, just using your power rule. Now let's think, if my r is about 3.837, right, if that r is positive, if I take a positive number and I cube it, it's positive. So all this chunk would be positive. And then, of course, 4 pi would be positive. So I'd have a positive number plus a positive number. I know if I plugged in a positive input for this value r, my second derivative would be positive. Right, so since the second derivative is positive and the first derivative was 0, remember, positive second derivative means concave up. First derivative being 0 means you have the horizontal tangent. I know the combination of those two facts guarantees that you're going to have a minimum at that point. So the second derivative test is a good backup. I really know that that's only a relative minimum, but since we only had the one critical point, and since there were no endpoints, I confirmed that that one critical point was, in fact, the type of a critical point that I wanted. It was a min. Since there were no other options, we know that it has to be the only min, therefore it's the absolute min. Right, so you always have to do something. If you can do the candidates test, you should. If you can't, typically you would do the second derivative test instead. All right, we're going to end with those two. The next time when we watch the next video, we'll do the remaining two optimization questions.